I apologize for taking a little long to get this thing going, but finally it's working. Um, so are you guys all excited about the iPhone 6 and iWatch?
No.
No? I am. Um, Samsung? Okay. Anyways, we started this example on last Thursday, and because it's a long example, so we stopped it. So what we're going to do is we're going to continue on this example, and we're going to finish up, and hopefully I have the time to give you another example today. Okay. All right. So again, a quick review. So it's a beam with two-dimensional loading. You have a distributed load on the surface on the XY plane, right? And you also have a concentrated load in the XZ plane. So you have concentrated load pushing it into the wall while you have a distributed load pushing down, okay? So now the question is asking, with all the geometries given, first of all, where's the maximum tensile and compressive bending stress? Because remember when we said we have an equation, right? Sigma equals to mc divided by I, right? So when you have bending moment happening on a beam, you have a bending stress developed across the thickness of the beam, right? And it's asking where the maximum tensile and compressive stresses are and quantified it, okay? All right, so let's look at A first. Now all we are doing is, let's see, we're using this equation over here, okay? So this equation tells us when you have a stress in extraction, you have two-dimensional bending, which in other words, you have two-dimensional bending moment, mz and my, right? And the amount of stress, you can just do superposition together, right? So we can look at them individually. We look at this term individually, and we look at this term individually, okay? So that's why we need to find an m, because y is the distance to the neutral axis, which is easy to find, half of the thickness of the beam, right? And the I is a secondary moment of inertia. It's easy to calculate as well based on the dimension of the beam, okay? All we don't know is what's the bending moment inside the beam. So therefore, our first effort will be finding the bending moment of the beam upon the two-dimensional loading, okay? All right. Okay, so first of all, we start with XZ plane, right? In XOZ plane, you have concentrated force of 100 newtons pushing down, and we're trying to find out what's the bending moment over here. So we start with equilibrium, summation FZ0, summation MO0, try to find out the reaction force because it's a cantilever beam, so therefore you have a reaction force going upwards, and also you have a reaction bending moment, MO, right? Okay, and then we find out MO is equal to 800, and we find out FZ is 100 newtons. So we have a shear diagram, and then we have a bending moment diagram like this. So we know maximum bending is 800 Newton times meter, which at the corner of where it's fixed, which is 0.0. Okay? Any questions so far? Okay. All right. The next thing is we want to see the constant or the distributed loading XY plane. So in XY plane, we can draw the same thing. So this is x-axis, and this is y-axis over here, and we have a distributed load with a magnitude of 50 newtons per meter. Okay, now again, if you take the reaction force over here off, you will end up to have one reaction force going upwards, RO prime, and in the same time, you have a bending moment, MO prime, which is compensated for the bending moment caused by this force over here, right? Okay. Now, when you have a distributed load, the first thing you do is you try to find out the equivalent load. Trying to find out the equivalent load over here. So this distributed load can be equivalent as a this orange force here, right in the center, with a magnitude calculated by 50 Newton times meter times total length, which I believe is 8. So let's say this is force F. So F equals to 50 times 8, yes, 400 newtons. And the location is right in the center. It is right in the center, 4 meters on each side, okay? All right, so therefore, when we say summation Fy is 0, now pay attention, this time the force is going y direction, right? Positive y or negative y. So summation Fy is 0, then we know O prime is equal to 400 newtons pushing upwards because this orange is going down, right? Okay, and also we have summation MO prime is 0. Therefore, this MO prime is just equal to this force over here times moment on, which is half only, 4. Okay, so 50 times 8 times 4. This is the force, this is the moment on. Therefore, that's 1600 Newton times meter. Okay, so once we have that, the next thing is we can draw free body diagram, and we can find out what's the maximum bending moment and what's the maximum internal shear force. Okay, so let's see here. First of all, shear force as a function of x. So see here, R prime equals to 400 newtons positive, right? And you have a distributed load of 50 newtons per meter. 50 newtons per meter. 50 newtons per meter. Therefore, it's going downwards with a slope of negative 50. So we automatically know this is 400, and then it's going downwards like this. Right? Because dV divided by dx equals 2q, which is negative 50. Although I didn't mention about positive or negative on the magnitude of the distributed load, but you see they're all going to negative y, so therefore it's negative, right? So you have a line start at 400, going negative 50, so at the end it's 0, okay? Because 50 times 8 is 400. All right, so I guess my handwriting is getting terrible again, huh? Okay. So next one is looking at the bending moment, Newton times meter. Okay, so first of all, you have a 1600. That's at the end, right? 1600. Now, we also know at the end where there's no bending force at all, so there's no shear force at all. Of course, it's going to end up at 0, right? So here's a tricky thing. Remember, we said dm over dx equals to v, right? So all of v, it's positive over here. And I have a number of 1600 Newton times meter. So it should start either at a positive 1600 or negative 1600, right? And also I know the slope is going to be positive because all these v values are positive, right? Okay, so that I automatically know if I use all the equations, it's supposed to start at a negative 1600. Why? Because you have positive slope, so therefore you're going to increase through the whole time, and then eventually ends at a 0. Now let's go back to see why it's negative. Okay, see here. So this force is going to make this beam rotate clockwise, right? So therefore, this MO prime actually is going to be what? Counterclockwise, right? So we know actually it is going to be counterclockwise. Okay, now here's something interesting. If we look at one point, any point, for example, over here. If we look at this point, you have a force going up, and you have a bending moment going downwards, right? So at this point, you are going to have a force going down, and you're going to have a bending moment going clockwise to compensate for that, right? Because at that red point, it is going to be under equilibrium. So therefore, the way you can think is say, hey, this bending moment at this specific point is negative, so that's why all these bending moments are negative. Okay, but by saying that, it doesn't mean in the future when you are taking a quiz or exam, if you have a positive over here going down to 0, I'm going to deduct some points from you. No, why not? Which I'll tell you later, because you can just see from the figure, right? So in other words, if you have a bending moment diagram starting from 1600 and then going down to 0, it's okay too, right? Because all we care is absolute number over here, okay? All right, let's see what else I need to mention. Oh, okay. So initially, this curve looks like a parabolic shape, right? So initially, it increased very fast, and then slowly it becomes 0. It's because the slope of this M curve is equal to V. Initially, V is a big number, so initially the slope is high. Then slowly the slope becomes less and less and less until 0. So you'll see a curve going this way, okay? All right. Okay, so like I mentioned, all we are doing for this shear force and bending moment diagram is we're trying to find these two things. This and this. 800 and 1600 Newton times meter. Okay? Alright, now a quick reminder. This, right? So probably we already know what's M based on what we did, the moment diagram, right? And like I mentioned, C is the distance to the neutral axis, which I'll show you. It's like right away you can get it. Another quantity we don't know is I, so probably we need to calculate I, huh? All right, so IZ equals to 1 over 12 base times height cubic. So base is 0.75, height is 1.5 cubic, and then that gives you 0.2109 meter the fourth. Okay, because if you look at a cross section of the beam, this is our z-axis, and the height over here is 1.5. The base is 0.75. Okay. Now, the way you calculate the IZ, or the area moment of inertia is always 1/12 base times height. So that tells you height plays more important role, right? So that's very easy to understand physically. Actually, anyone has a ruler here? A plastic one or a stainless steel one? A ruler? You have a ruler? Okay, can I borrow that? What, this one? Oh, do you have a different one? Traditional shape? Oh, this one don't use ruler, huh? Okay.
Hey, Professor.
Oh, you have one? Oh, awesome. Okay. So, because it's hard for me to remember, so what I always do is, area moment of inertia is just a quantity to calculate how easy it is to bend, right? Now imagine this ruler over here. So if I'm going to bend this way, it's easy, right? I can bend it with my hand. So in this case, the base is the width over here, okay? And the height is just the thickness. So the base is big, but the height is so small. So 1/12 b times h cubic. This h is a small number because how thick is this ruler? Probably half millimeter, right? And how big is this base? Probably about 1 inch, so about 2 centimeters, right? So 2 centimeters times 0.1 centimeters, a small number. So I can bend it, easy, right? What if I do this way? Pretty much impossible, right? I'm trying to bend it up. So in this case, the base is 1 millimeters, but the height is 2 centimeters. So in this case, you have height of 2 centimeters, 2 times 2 times 2, that's 8. That's a big number, right? Because this time the height has a power of cubic. So it's therefore this area moment inertia is a big number. So therefore, under the same bending force I have applied by my hand, I cannot bend it. Make sense? Yes. Okay. All right. Thank you. All right. So that's the same thing. And for IY, you can calculate in the same fashion. 1/2 base times height cubic. 1/12 base. Did I say something wrong, or did I break your ruler? No. Okay. All right. So in this case, it's the other way. So the base is 1.5. The height is 0.75. Okay. Now this is IY. This is IZ. Alright, so I have another two numbers which will be useful for my calculation. Basically, that tells you this area moment of inertia is a quantity to measure how easy it is to get a bend under the certain amount of applied moment, right? Okay, let's see. All right. Okay, and so one last thing is we need to find out the distance to the neutral axis, right? So, okay. That's very easy, and I'm just going to draw a picture over here to show you under everything okay? Anything wrong? Or you guys didn't get to write down the notes? Okay, so this is our beam, right? And this is coordinates. All right, and this is force. Okay, so by looking at it here, actually, let me just turn it. By looking at here, if we only look at the XY plane, which has the distributed load over here, so you are going to see a load like this. Okay, now still keep in mind the bottom or the point O is fixed, while the other point C over here is free, right? So it doesn't have any constraint at all. Okay, now you can imagine, so under this load, under this distributed load, if I'm just trying to push it down, where is maximum stress at?
Where it's mounted?
Yes, that's right, that's absolutely right. So let me give 3 points. For example, this is point A, this is point B, and this is point C. So where is the maximum stress at if I push it down? Or hit on at which line? At AB, right? Should be this line, maximum tensile stress, right? Because if we push it down, this top is trying to separate away from the wall, right? And let's say this is point D over here. So where is the maximum compressive stress at? CD, right? Very good. Should be CD over here because it's trying to push into the wall, right? Because in the center, at the neutral axis is nothing, right? Top will be on the tensile, bottom will be on the compression. So of course, the further it is away from the neutral axis, the more stress it'll be, right? Okay, so very good. Let's see here. Let me try to draw a cross-sectional view for you. I want blue. In this case, let's see, this is Y, and let's just take a cross section, right? So, because in the dimension of Y, the maximum over here is 1.5. is from top to bottom. So the maximum distance to the neutral axis should be half of it, which is 0.75 from top to the neutral axis, right? So this is our maximum neutral axis under this loading condition. Make sense, right? Okay. All right. So let's try to see the other case. The other case, I'm not going to draw the boundary conditions because everybody already know. Okay, so again, you have this. So this time, the concentrated force is pushing into the wall, right? And again, I have x-axis and y-axis. So in this case, bottom is fixed, right-hand surface is free to go, and you have a force pushing into the wall, into the negative z direction. Now, I still say I have a point A, B, C, D. A, B, C, and D. So in this case, on the force that's pushing into the wall, where the maximum positive tensile stress will be at BC, right? And how about compressive? Should be 80, right? All right. Okay. Now, let me draw this cross-section view. Z and Y. So because the length along Z is 0.75, so half of it will be 0.375. If I did my math right. Okay. So these two loading conditions, as we mentioned, we can consider them separately, right? Now, the question is asking where the maximum stress for both tensile and compression is, right? Both force will cause stress in the tensile and compression, and the total effect will be superpositioned, right? They'll be added together. Now, on A, B, C, D, the surface is 2 points. They are very special. What's the special about? They lies on both red lines for the case of distributed load and a concentrated load. At the same time, there's another point. It lies on both maximum compressive stress and under the distributed load, and also maximum compressive load under the concentrated load. So these 2 points are point B and what? Point D, right? So point B is on the maximum tensile stress of AB due to the distributed load, but point D is under the maximum compressive stress line on the distributed load. At the same time, they are on the maximum tensile and compressive loading because of the concentrated load as well. So that tells you probably, very possible, maximum tensile will be at a point B, maximum compression is at a point D. Supposed to use a different color. Compression, I use blue, and tensile, I use red. Make sense, right? Yes? Two-dimensional loading, okay? All right. And we also find out the distance to the neutral axis, which is Z in the equation, right? So, okay, so let's add these together. Okay. So let's say maximum tensile stress occurs at point A, which is caused by both loadings. Which is distributed and concentrated. Okay, now therefore stress along the x direction at a point A equals to mz times y divided by iz plus my times z, which is at point A, divided by iy. Okay, mz, which is what we calculated, 1600. Ya, half distance to the neutral axis, is also what we calculated. Iz, we have the number 0.2109 plus my 800 times za 0.375, iy 0.05273. So equal to 11,380 Pascal. Yes.
It is not point B, right? Maximum is high stress.
Oh, I'm sorry. Yes. Thank you. Okay, so it's at a point B, and all you need to do is find the numbers and then just plug them into it, right? Okay, so here's one thing I want to mention. Now, for the distributed load, once you push it down, you are going to have tensile stress on the point B over here, right? Let's see how am I doing? A, B, C, D. Okay. Okay, so because due to the distributed load, the tensile stress on AB should probably go this way. Agree? Right? Okay. Now, if you have a concentrated load, trying to push it downwards on the BC point of view, only look at BC, alright? Let me try to use a different color to separate it. Concentrated force. It's going to cause stress going in that direction. If I say this is sigma x prime, and this over here is just sigma x double prime. Now, as you would imagine, at point B, the stress is these two added together, right? Now, both tensile stress is pointing to the positive x direction. That's why answer is sigma x. Okay, makes sense, right? And then by looking at this stress, concentrated force in red color, causing stress in red color pointing to positive x. Distributed load has black color, so it's causing stress of black color pointing to also positive x direction. So only at a point B, the black and the red added together, right? So that's why it's called a sigma x at a B, because it is pointing to the x direction, and at a point B, it's just equal to the superposition of these two things. And like I mentioned, see, all I care is amount of the banding, right? So I just use 1600. I don't care about it's positive or negative. because from this figure, I know both the positive x, so I add them together. And also this my, all I care is the absolute value, 800, and that's what I used, right? And then yb and the zb, of course, they are always positive number because that's a distance, right? And the iz and iy, the positive numbers. So I think in the textbook, it has a negative number over here because of the definition of the bending moment. But I don't really like it because it's getting confusing. Because by looking at these figures, both black and the red are pointing to the same direction. Of course, I can just add them, right? So I think this is easy, and that's why I didn't really follow the textbook over here. So I think that might be easy to understand. You guys agree? Or not necessary? Okay, sure. Whatever you want, as long as you can get the right answer, okay? All right. Okay, so the next thing will be we want to look at where's the maximum compressive stress, right? Okay, compressive stress, it's the same thing. Compressive stress of course the maximum will be at a line CD over here. And then like I mentioned, it's going to at point D, it is because when you have concentrated force over here, the maximum compression is at AD. So this D is on the both line, so you can add them together, right? Now, a good thing about this example is everything is symmetric. So neutral axis is right in the center. So actually, I automatically know at point D should equal to negative of point B. That should equal to negative 11,380 Pascal, right? Because everything is symmetric, okay? And compressive stress is just nothing but the inverse, just opposite of tensile stress. So just take the negative, that'd be good, okay? All right, so you guys have any questions regarding question A so far? No? Okay. All right, so the next question is, it's asking if the beam is a solid circular cross-section with diameter D equals to 1.25 meters. Okay, so same loading condition, but the only thing different is we change that to a circular shape. Okay, all right. Now this I'm just going to show you. The equation we need to use is the maximum stress equal to 32 pi to the cubic my plus mz 1/2. Okay, so this is the equation we need to use, and I didn't really mention initially because I figured it's just easy if I mention that while we see the example, so you can just remember right away. Okay, all right, so 32 pi d cubic times 800 square plus 1600 square, sorry, missing a square over here, square root and a D diameter is 1.25. So therefore you plug in the numbers, 9329 Pascal. Okay, that's the answer. Now, the reason why I think question B is important is, see, compare these two numbers. So when you have a circular shape beam, tensile is 9329, while compressive is negative 9329, right? So if you look at this absolute number here, maximum tensile we have a rectangular, it's 11,380, but if you have a circular shape, it goes down to 9329, right? So that tells you when you have a beam, if it's a circular shape under the same loading, probably you're going to see less maximum stress, which means a less chance of failure, right? Okay, so anyways, that's about it for the example. Now I'm very positive you will see a very similar question or problems in the quiz and the exam. All right. So make sure you understand this example. We have two-dimensional loadings. How do you do the analysis, and what's the steps? So make sure we are all fully aware of this example. Okay. All right. Have any questions so far? Okay. All right. So the next topic I want to cover is called torsion. So torsion is a little different from bending. It is another type of deformation you'll see a lot in a beam. Yes.
Question on that last point you made.
Yeah.
Does it make a difference that it's circular versus rectangular, or is it a function of the cross-section area?
In terms of what?
In terms of the stress that you develop with the forces that are applied. Is it in terms of the cross-section or in terms of the shape?
In terms of a cross section.
Okay, so that's a heavier cross-section on the circular one, right?
Yes, it is, because it has more area under the same dimension. If you use the same amount of materials, of course, circular will have a less area, right? Because of circular, ideally, it's maximized for the least surface area to volume ratio. So, of course, it is, yes.
Okay. Thank you.
Yep, you're welcome. All right, so torsion. So fundamentals of torsion, just a quick review. It's when you have a beam that's fixed at one end, and you set up your coordinates like this: x, z, and y. For example, the end is fixed. Okay, and so end is fixed, and I'm trying to apply a pair of torque. Try to twist it. Total length over here is L. And if it has a fixed end and it have free end, and you have a coordinates like x, y, and z set up over here, total length L, we're trying to have a pair of torque apply on it. Of course, it's going to twist it, right? So it's different from bending. You don't see the curvature, but in the same time, you see a deformation at the front surface because the top and the bottom surface is fully fixed. So you see a twisting on the front surface. Okay. So the way we can quantify it is we looking at the front surface. So Y and Z. If we say initially, before the force is applied, you have a point A, and after the torque is applied, it changes to A prime. This angle over here, we call it theta. Okay. All right. Now, theta is quantitatively defined by the amount of torque you apply, the length of the beam, and modulus of rigidity, and also polar second moment of inertia. Okay. So this T over here is torque, Newton times meter. Torque actually is very similar quantity as moment because they have the same unit, Newton times meter, right? Which next example I'm going to show you, we have three-dimensional loadings, some torque and a moment, they're interchangeable, okay? So L is the length, G is modulus of rigidity. And J is polar second moment of inertia. Okay, so it's also easy to understand. See, the higher the torque you apply, of course, this amount of change, this theta will be higher, right? Now, the longer it is, the more it'll be. Why? Because think about this. If this beam is really short, we apply same amount of torque, it becomes more rigid. It's kind of like when you have a beam. If it's really long, it's not that rigid if you have a concentrated force in the center, right? It's the same idea. And the G is modulus of rigidity is very similar to Young's modulus. If this thing is made of rubber band, easy to bend. If this thing is made of stainless steel, of course, it's harder to bend, right? So, and the same thing, it's hard to twist. So another thing is J, which is a function of the geometry. The bigger the diameter it is, of course, it's harder, right? So basically, that's it. And here's also another quantity that's interesting. So if I say on this cross-section area, I have an arbitrary point with a radius of rho. And the total radius of this entire cross-section is r. So this shear stress developed throughout the cross-section for a round bar in torsion these stresses are proportional to the the distance to the center, which I say here is radius r. Oh, sorry, it's radius rho. Is tau equals to t rho divided by j. Okay, so that's also easy to understand. It's very similar like a neutral axis idea. So if I twist it, on the outside surface, it has most shear stress. At the rotational center, for example, I say this is 0.0, it's not going to have any shear stress at all. Okay? All right. Tau max equals to T times rho max divided by J. In other words, equals to T R divided by J, because maximum rho just equal to R on the surface, right? So that tells you on the surface of the rod has a maximum shear stress, but in the center it has zero stress, shear stress wise. Okay. All right. Now that's for circular cross-sectional area. You have this. If you have a rectangular, this is the equation we need to use, but I don't think I'm going to have any example requires you to use this definition, just to let you know. All right.
What are you having the top?
Hmm?
What are you having the top? 1 times E? What is it?
Here,
Plus, yes.
1.8.
1.8.
Yeah. Okay. All right. So a quick review. Wexler tells you if you have a cantilever beam, you have a torque applied, then shear stress is going to generate it, right? Actually, if you want, I can do this for you. So torque applied. Torque on top and bottom. I mean, there's another torque at the end, but I'm only going to show you the torque in the front, right? So the amount of shear stress should equal to this. Kind of like how we learned the neutral axis concept, right? So if it is right in the center of the rotation, then there's no shear stress. If it is far away on the surface, the stress is the highest. It's linear relation 2, right? That's why we have this equation. See the tau? It's tau. Okay, all right. So that's pretty much it. And we have class until what time? 4:20, right? Okay. Huh? 19 minutes? Okay. I prefer not say this example because it's relatively speaking long and I want to be consistent. So what I'm going to do is on Thursday, I'll give you an example of a torque and a moment combined loading, okay? So the next 20 minutes, I'm going to show you some new concept, which doesn't require a big example. So we can finish things up a little quickly on time. Okay, so another thing is, like I mentioned, in our mechanical design, one of the important components is the beams, right? So when you have load on a beam, another thing is deflection and stiffness. Okay, so again, we look at simply supported beam. So if you have a simply supported beam, at one end is fixed, the other end is free to go, right? Okay, now if I apply a force right in the center, you would imagine it's going to see deflection, right? Imagine this is a piece of wood, and then both ends are fixed. I use my finger to push it down. It's a thin piece of wood, okay? So it's going to deflect like this, right? Okay, so the maximum distance is definitely in the center where the force is applied. But to be general, I say the vertical distance between any arbitrary point to before and after the loading is y, and the total length over here is L. So on a small force and small deflection, this y and f they have linear relationship. All right, so 10 newtons, 10 microns, 100 newtons, 100 microns. So they're linear on a small deflection and for a relatively speaking long beam. Okay. All right. In this case, the beam is long. Now, sometimes you may ask me, hey, how do you define long, right? We're not liberal arts. We're engineers. We like numbers, right? So long this is L divided by A is bigger than 20. So it tells you when you have a beam, the length divided by the cross-sectional area is more than 20, then you can call it a long beam, okay? If it's less than that, then we call it a short beam, okay? All right. Now, that tells you when you have a long beam, you have a linear relationship between the force applied in the center and the displacement, okay? All right. Now, also, since we mentioned about long beam, of course we have short beams, right? So when the beam is short, still do the same thing. Force applied to the center. You will also see displacement across the original and the deformed shape, right? Now, in that case, what you have is you have a non-linear relationship Fy. So this is for short beam. Now, when it's short beam, usually L divided by A is less than 20. Okay, so initially, the amount of force you apply is relatively speaking easy to have a displacement. Now it becomes stiffer and stiffer. That's short beam, all right? So that's a phenomena for short beam. Okay, so just be aware of those things. Okay, now for most of the case we have here we only consider linear F and Y relationship. So now because they are linear, therefore one of the quantity we're interested in is this tangent alpha, which equals to F divided by Y, right? Okay, because they're linear, this slope is constant across the entire loading conditions. Then when it's constant, tangent alpha is also a constant value. We give it a name, which is K, and the K we all know is called spring constant. because they're very similar as spring, right? When you compress a spring, it's going to shrink, and the force that you applied and displacement, it's linear, right? Okay, so for any of the beam, it also has spring constant to quantify the amount of force you applied and the vertical displacement you'll have. Okay, all right. So the next thing I want to mention is tension. Compression. And torsion. Oh, just a quick reminder. Remember we've said we're going to have 3 projects, right? So very possible since we're already in pretty much mid-September. So I am going to assign the first project on Tuesday, right? So on Tuesday, I will assign you into 12 groups. We have about 62 students, so 12 groups. Each group will have 5 students, or 2 of the groups will have 6 students because we have 62 students. So, and I'm going to give out the description of first project. So just be aware of that, all right? So make sure you show up in class if you can on Tuesday, all right? Okay. All right. So tension, compression, and torsion. Now again, like I said, I will assign the groups randomly, and sometimes actually the department will help me to assign the groups. So you cannot choose your group members on your own. All right. So you have to work with some people I assign you to. I haven't had any case change of group members, which I don't want to do that. And the reason I already told you, right? Okay, so once I assign a group, it's set. You have to stick with the group for the entire semester. Okay, all right. So,
Does that say local?
huh? Okay. Total. Total extension or contraction. Of a uniform ball. Imputation or compression. Is delta equals to F times L divided by A times E. So this is when you have a beam that's under loading. And the force is applied. The maximum displacement is called delta. So F times L divided by A times E. This is what the total displacement is defined. And also we know the displacement is in the y direction, right? So we can also say the delta is y. Okay, so K is a quantity to relate to the force applied and the displacement you have, right? So therefore, we can define this K equals to AE divided by L, which is very similar to F equals to K times Y, like what we see before, right? F equal to K times Y. So basically, I have F, I keep F over there, and the delta is just Y because it's in Y direction displacement, and everything else is just K, okay? So, in other words, the spring constant of a beam is a function of a cross-sectional area, it's a function of a Young's modulus, and it's also a function of the length, which makes sense. Why? imagine the beam, right? The longer it is, the easier it easy to get bent, right? So if it's really long, hang there, you point into the center, the beam, relatively speaking, it's not stiff, so it's easy to get displaced. So the longer it is, the less the spring constant it is, right? Young's modulus also makes sense. If it's a wood beam, you can displace it, but just use your hand. But if it's a stainless steel, it's more rigid, so the spring constant is proportional to Young's modulus. And a cross-sectional area for sure, right? If you have a really skinny beam compared to a very big diameter beam, of course, big diameter beam is going to have a higher stiffness, right? Okay. All right. So I am going to stop here because that's pretty much all the stuff I want to cover. Thursday we'll have an example. Okay. All right. See you guys on Thursday.